Right, so our next speaker this afternoon is Tien-Cuong Dinh from the National University of Singapore, who will speak about complex Hénon maps in higher dimensions.
Thank you very much. So let me thank the organizer for this invitation. So I'm very, very happy to be here. And actually, this place is very similar to my hometown, except that my hometown is smaller. And also the food is less spicy. So thank you again. So I'm going to talk about complex Hénon maps in higher dimensions. So I would like to focus on some techniques that we developed to study complex dynamic in higher dimension. And then I choose to talk about Hénon maps because it's simpler for the presentation. But okay, but the technique could be used for other families of maps. Okay, so a little bit about the history of Hénon maps. So it's go back to the famous Lorentz attractor. So here's the Lorentz system is given by the ODEs in R3, which is very explicit and simple. So I have three ODE like that. And by some typical orbit, it look like in this picture. But the system is chaotic, and I can show you some little movies that I saw in internet to see what. Oops. I want to show you what happened. I mean the similarity with the Hénon map. So you have two orbits which are starting from 2 points which are very close each to other. And at the beginning, you see that the two orbits are similar, but very quickly, see that the orbit will be different. Yes. So if you don't care about the exact position of the points, then basically the blue set and the red set are more or less the same. So this is due to the ergodic theorem. But if you care about the exact position of points, then the orbits are quite different. So it looks like that. Maybe I don't need to. It's more than that. So I come back to the Hénon map. So one idea to study this dynamical system is to use some transversal. Sigma is a plane of dimension 2 in this space of dimension 3. So you consider a point X on this sigma, and then you follow the orbit of the going outside sigma. And the first time when you go back to sigma is another point that we denote by fx. So we have a map f from some subset of sigma to sigma, like that. If you continue to follow the orbit, then the next time you come back to sigma will be fx, and the next time is ffx. So in order to study the system, you can focus on the iteration of f on sigma, and this reduce the dimension to 2, and then somehow you forget the flow direction, which so okay, it simplify a bit the problem. And then Pomo and then Hénon try to simplify the map F to get a simpler model, simpler map, which give you a complicated dynamical system. And then finally, they found this map, the so-called Hénon map. So it take a very any polynomial of degree at least 2, for example, x squared plus c, and some constant b not equal to 0. And then the Hénon map is given by this formula. So p of x plus y and b times x. Okay, which is important here that you focus on x and y, and you see that you exchange the position of x and y here. It's become y and x. So this makes the system complicated. And And the inverse of F is easy to check that the map is invertible, and the inverse of F is also a polynomial automorphism given by a similar formula, except now the polynomial is on the right side. And x, y, you also permute x and y. So it's very similar to some kind of map here. So here we want to study complex Hénon map. So it's given by the same definition. So the same formula, except now I use the Z and W complex variable. So the same formula for F and the same for F minus 1. Okay, so what do you expect here? So take a very simple situation of B is almost equal to 0 and W is equal to 0. Then what happens? So you see that F of Z0 is equal to PZ, almost equal to PZ0, and F square is like that, and Fn is like that. So you don't expect that the dynamics of Hénon map is simpler than the Fatou-Julia theory. It's likely more complicated. Okay, so this is a slide for this beautiful theory that we already have seen in the last talk. Okay, so let me skip this and go back to the Hénon map. So we are in dimension 2 complex, which is 4 dimension real dimension 4. So I cannot draw the complete picture. So here is this classical picture for the modulus of Z and modulus of W. Okay, so you can choose a big real number R, and then you divide this space into 3 parts. So here's the modulus of Z is equal to 1, or R. Here's the modulus of W equal to R, and here's the modulus of Z equal to the 1 of W. So the point that you see here, this point, is actually a real torus because we are in dimension 4 here. Yeah? But okay, it's just to remember that we are not in dimension 2 here. Then if you consider any point in this right-hand side domain, then the orbit will go to infinity, and it's go to infinity exponentially fast. It's very fast. Okay, so the dynamic here is clear. So if you are somewhere in this square, there are 2 possibilities. Then maybe after some time you enter the domain on the right side, and then you go to infinity exponentially fast, or you stay in this square forever. Okay. So if you enter to this domain, then you go to infinity. You have no choice. Otherwise, you stay in this square forever. So on this upper domain, there are 3 possibilities. So either you go from directly to the domain, you go to the right-hand side domain, and then you go to infinity very quickly. Or you first go to the square, and then stay here for some time and go to the right-hand side domain and then go to infinity. Or you go to the square and you stay here forever. Okay, so you see here that for every orbit, either you go to infinity exponentially fast, or you stay in this square forever after some time. You don't have a situation that some orbit go closer to infinity and go back, and then go to infinity again and go back. You don't have something like that. So this tell you by this picture, which is not easy, difficult to check. Okay, so so now K plus is the set of points such that the orbit doesn't go to infinity. So it looks like that. So it cannot have intersection with this domain. It should belong to this domain. So if you take any point here, the orbit should be bounded in C2. Yeah. So this is a set K. So this is a closed set, which is invariant by F, by the dynamics. This is just by definition. You can apply the same study for the inverse of F, and you get another set, this one, K minus. So the negative orbit of every point from K minus doesn't go to infinity and stay in banded in C2. Yes, so the picture looks like that. The intersection of the two sets is also invariant and is a compact subset of the square you see here. Okay, to study this dynamical system is more convenient to work with not directly with C2, but with a compact complex manifold. So for this reason, we try to compactify C2, and the simplest way to compactify C2 is to put to glue C2 at infinity with some Riemann sphere. So the infinity that you see here is the Riemann sphere, and if you do so, then the picture becomes like that. So the set K plus go to infinity and touch infinity at exactly 1 point, I plus, and K minus go to infinity and touch infinity exactly at 1 point. And the key point here is I plus and I minus are disjoint, different for Hénon map. This is the point of view of Sibony, and that this is the reason that he introduced the Hénon map in higher dimension. Okay, so the picture will be similar to this one, but except that it's in higher dimension. So let me introduce this here. So you consider an automorphism F from CK to CK, a polynomial automorphism, and then you extend it to the simplest compactification of PK of CK, which is CPK, is similar to the K of dimension 2. You glue something at infinity and look like a sphere, look like a complex sphere or something like that. A compact complex manifold is very nice, homogeneous, and so on. But if you compactify your manifold, then the map is no more holomorphic everywhere. So on CK, the map is holomorphic, but okay, sometimes it's become holomorphic on PK, but it's not interesting for us. But we assume that it's not holomorphic on PK. Then you have some singularity at infinity. So for the map F, you have I plus, which is the indeterminacy set of F, and I minus is the indeterminate set of the inverse of F. So so it's similar to the case of dimension 2, except now I plus and I minus are algebraic subset of infinity. So at infinity, you have some hyperplane, projective hyperplane, and you have two algebraic subset on H infinity, which yeah. And the definition is very simple. So we say that F is Hénon map or regular automorphism and so on if the intersection of I plus and I minus is empty. So it's a very nice definition because the hypothesis is so simple. You just check it one time, and then you can develop the theory. You don't need to check it for every iterate of F, just one time at the beginning. So in dimension 2, according to Friedland and Miner, in dimension 2, any non-elementary automorphism is conjugate to a Hénon type map like that. So you don't have other interesting dynamical system to study in this dimension 2 for automorphism, of course. And it's not true in higher dimension, but still it's a big family of automorphism. So also it's not difficult to prove that there is some number P, integer P, such that the dimension of I plus is K minus P minus 1, and the dimension of I minus is P minus 1. So yeah, so the dimension is like that. Okay, so here's the picture. It's quite similar to the case of dimension 2, except that at infinity now you have disjoint algebraic set. of some dimension, and k plus is like that, k minus is like that. It's quite similar, except that the dimension is not 0 for I plus and I minus. Okay, so same definition for k plus, k minus, and k. Okay, so let's go ahead. Okay, I have to introduce a notion that we need here. This very quickly, this very quick introduction. I will come back to this a little bit later. So, starting example is that if you have a point A, then you can associate to delta A is a Dirac mass. So this is a probability measure. So you can say that a point is a particular case of probability measure. Or you can say that probability measure is a generalization of points. Okay? So positive closed current is the same in higher dimension. So instead of variety of subvariety of codimension P or dimension K minus P, you have a generalized subvariety, which is called positive closed current. I will come back to this a little bit later. Yes, yes, yes. Complex subvariety. Yes. Okay, so so here's the first theorem due to Bedford, Lyubich, Smillie, dimension 2, Fornaess, Sibony, dimension 2, and Sibony and myself in higher dimension. So in K plus bar, you have only one positive closed PP currents G plus of mass 1. Of mass 1. And so if you want to take an example of measure, then you have only one set which satisfies this, is 1 point. If you have 1 point A, then you have only one probability measure which support in A. This is a Dirac mass and A. You have only one measure. But in higher dimension, situation is more complicated. So for K plus here, you have only one positive closed current of by degree PP of mass 1. So let me come back to this picture. So imagine that you want to put inside this red set, you want to put a compact Riemann surfaces. You cannot do that. There exists no compact Riemann surfaces inside this set, but you can put there a positive closed current. This is possible, but you have only one choice. You have the unique choice for this. So this is the theorem. Actually, it's true for higher dimension. In this picture, if you want to put here positive closed current of right dimension, you have only one choice. This is a theorem. Okay, and you have no algebraic subset in this K plus. Okay, so this is the first statement, and then automatically this should be invariant by F, because otherwise you produce new one. So you have the T plus, and the pullback of F by T plus is equal to some degree D some T plus. You have no choice, because if you don't have some identity like that, you can produce another one by pullback T by get another one. Okay. Next statement. If you take a complex subvariety of codimension P, which is generic in a very precise sense, if you assume that the intersection of V with I minus is empty, so most of them satisfy this condition. You take a subvariety like that and you pull back by F. You pull back by Fn. And you have to normalize this properly, because the degree increase, the volume increase. But if you normalize this properly, then it's convert to T plus. This is not surprising, because I come back to this example again. Assume that you have a sequence of measure, probability measure, mu n probability measure. And you assume that the subbox of mu n go to A, go to the point A, then you have no choice for the limit. So mu n should go to the Dirac mass at A. Simply because you have no other choice for the limit, it should be the Dirac mass at A. Because at the point A, you have only one probability measure. Then if you have a sequence of probability measure like that, the limit should be delta A. But what is important here is that the speed of conversion is exponential. So the conversion is very fast. Okay. So maybe I precise here the notion of the convergence, the speed of conversion. So for measure like that, so mu n go to mu exponential fast, mean that okay, I skip some detail, but for every phi holder, phi alpha, you have that mu n phi, the integrand of phi by mu n go to mu phi exponential fast. You can also introduce this in an equivalent way. You can also introduce some distance, some notion of distance between mu n and mu, and you can show that the distance go to 0 exponential fast. So this you can do also. For example, Wasserstein distance and the other distance. But okay, so for current, you have the similar statement. I will show you a little bit later. Yeah, so the conversion is exponential fast. And the same statement is true for f minus 1. So I forgot to say that the current T plus has some complex structure, geometric complex structure. So it's weakly laminar is composed by small pieces of complex manifold. Yes, so there are many work on laminar currents, including the work of Romain, Dujardin, Detelin. And the second property, and the first property can be seen as some kind of unique ergodicity for T plus, for currents, or some rigidity for K plus, if you want. The second property is some equidistribution property. You have similar result in different settings, including the work of Tien-Cuong Yan, Faber Johnson, Taflan, and other people. Okay, so this is the first statement. Okay, so if you don't like currents for the moment, let me show you some consequence, which is easy to see. So assume that you take some generic subvariety of the same degree for simplicity, for example, some linear subspace V and V prime, and you choose a big N and you pull back them by Fn. So you have some algebraic set of higher degree, and if U is a nice open set, I'm not going to the details here, but if U is a nice open set, then you consider the red set here, which is of dimension k minus p, and a blue set also dimension k minus p, and you compare the volume of them, volume of 2k minus 2p dimension, real dimension. You compare the volume, then you have more or less the same volume. This is the consequence of the equidistribution. And this picture will be, I mean, exponential fast. If n is going to infinity, you see that exponentially quickly to get this kind of consequence. Okay, so let's go to the next theorem. So now imagine that T plus is a variety of same dimension, k minus p, and T minus is another variety of dimension p if they are in a good position then the intersection should be a finite set. And at this, at the point of this finite set, you can put Dirac masses, and that the sum of the Dirac masses will be the intersection of these two currents. So more generally, in a good setting, you can define the intersection of two positive cross current of good dimension, and you get here you get a probability measure. You can do that here. So it's similar to taking intersection of subvariety of good dimension and in good position. So in this case, you have an invariant probability measure, and it turned out to be the unique invariant probability measure of maximal entropy. Is exponentially mixing of own order, is hyperbolic, and it satisfies the central limit theorem. And certain period points are equidistributed with respect to mu. Okay, so you have this property. So let me go to the a little bit to the details of this statement. So the ergodicity that okay. So because the dynamic on the small Julia set is chaotic, to study it, we want to use the point of view, this point of view. So we want to test the system using some functions. So here we're going to see with two functions, phi and psi, with some regularity, Holder will be enough. So let's say phi and psi are Holder test function. So you consider the orbit of some generic point x. So you take the Birkhoff sum phi x, phi fx, and so on, and you divide it by n. Then by ergodic theorem, this converges almost surely to the expectation of this variable. So which means that the integrand of phi with respect to mu. So this is the ergodicity of the measure mu is like the law of large number in probability theory. Okay, so so the measure is ergodic, satisfies this condition. So the exponent mixing means the following. So we know that this random variable phi composed with fn, you have a sequence of random variables here. With respect to the probability measure mu. So this sequence, we know that these random variables are not independent. If it's okay, but if they were independent, then we have the integrand of phi composed with fn, for example. So if it's independent, then this should be the product of the integrand of phi composed with fn and product with the integrand of psi. But because mu is invariant, so it should be equal to mu of phi times mu of psi. So if this random variable were independent, then we would have this. But actually, we know that it's not possible because they are clearly dependent. But still, the system is going to forget the dependence very quickly. So these are exactly the notion of exponential mixing. So this integrand converges to this one exponentially fast. So this is a the exponential mixing of order 2, but this is true for any order, which means that you can, instead of 2 functions, you can put more functions, more than 2. Any number of functions, you have a similar statement. Okay, so the last statement, which means that the central limit theorem. So if you take this sum, phi x, phi fx, and phi of f n minus 1x, you remove the expectation, and you divide it, you normalize this by a good factor. So the good factor here is 1 over square root of n. Then it's going to converge in law, so weakly to a Gaussian. So this is similar to the central limit theorem in probability theory. So the measure mu satisfy this condition. Okay, so now I come back to the technique that we developed for positive closed currents, and then I give you more details about positive closed current, but I'm going to avoid the formal definition because it's not necessary to introduce here. It's too technical. So this theory developed by Okay Lelong in the year 50s, and there are many contributions by many people, including those people: Benson, De Mailly, Hoffmander, Sibony, Skoda, and many other people. And this is a quite powerful tool in complex analysis, complex geometry, and dynamics, and also population theory. So as I said before, this is just a generalization of the variety in some sense. Similarly to the probability measure, which are generalization of points. But however, we are in higher dimension. For measure, we are in dimension 0. So it's not very interesting to talk about intersection in dimension 0. But in higher dimension, the intersection become more important. So I go to detail of this. Okay, so it's a little bit more about the definition of positive closed current. So we go back to the case of probability measure. So for simplicity, we work on compact manifold, take Kähler compact for simplicity. So you can stay on this positive space CPK, simple compactification of CK. So positive measures are exactly positive closed current of maximal by degree. Maximal by degree KK. K is the dimension of the manifold. Is a maximal by degree, which means that it's a maximal codimension, minimum dimension, dimension 0. Dimension 0, codimension K, which is maximal. Codimension and by degree is the same. Okay, so we consider a finite combination lambda I AI. Lambda AI are points in X. Lambda I are positive real number. We assume that the sum of lambda I is equal to 1. So here you have a so-called effective 0 cycles of degree 1. Effective because the lambda I are positive, 0 because it's of dimension 0, and degree 1 because the sum of lambda I is equal to 1. So you have this formal cycle, combination, finite combination of points with positive real coefficient. So we have a correspondence between this thing and the probability measure, which is the sum of lambda I and the Dirac mass at AI. So this is a correspondence between effective 0 cycle of degree 1 and probability measure here. Okay, this probability measure has only atoms and a finite number of atoms. Okay, so this is a particular case of probability measure. So in this way, you see that the space of all effective 0 cycle of degree 1 can be embedded in the space of probability measure. But this space of probability measure is a compact space. So somehow this is a way that you compactify the space of effective 0 cycle of degree 1. Okay. So then to see this object, you can use the duality point of view, which means that you have to test the function. You have to test function. So if you have a continuous function phi, so you have a test function phi, then you can consider the integrand of this function with respect to your measure. So which means that given a measure mu, you have a linear continuous form on this space of continuous function, which means that you can identify your measure mu as an element in the dual space of this functional space. Okay, so you can see this object by duality, by testing function. By testing function, and okay, so as example, you have the Dirac mass. So if you have a Dirac mass at A and you want to test the function phi, you just have the value of phi at A. Okay, and another example is the smooth case. So you take a positive differential form, KK form, the volume form. Let's say volume form of integrand 1. If you have a volume form of integrand 1, then you can define the probability measure is like a Lyubich measure. Okay. If you have volume form, just take the integrand, then get the Lyubich measure here. Actually, this family of smooth measure is dense in the space of probability measure. So which means that given any probability measure, you can approximate it by volume form. This is a classical theory of using either convolution or other techniques. You can do that. Okay, so this is a picture for probability measure. So let me go to the currents now. It's not a definition, formal definition, but it's a quick introduction. So for currents, you just replace function by differential form. So instead of using function, you use a differential form, and then you have currents. So here you don't use the own currents, but you use some positive cross currents. So the picture is similar. So assume that you have now, instead of points, you have a subvariety of codimension P. So VI is a subvariety of codimension P, positive, and the sum of lambda I and degree of VI is equal to 1. Then you can consider this finite combination, lambda I VI. And for this combination, you can associate to this operator. So the sum of lambda I and the integrand on VI. So it's similar to taking the Dirac mass at a point. Now you take the integrand. So for Dirac mass, you test function. For variety, you test form. So it's you take the integrand of form on variety. So this is this correspondence between this cycle and this positive cross currents. So here is a more precise statement. If you have the test form of right degree, then you associate it to the sum of lambda I integrand of phi on this VI. It's very similar to the case of Dirac masses. So then you have the space of effective cycles of degree 1 and of codimension P in X. And I didn't define exactly what is a positive cross current, but you can embed it inside the space of positive cross PP current of mass 1, which is now a compact set. So this is a way, some way to compactify the space of cycle. And you can see this using test differential form phi, which means that you again use the duality point of view for currents. So as example, you have this combination of varieties, but you also have a smooth positive closed differential form, so similar to the volume form, but now it's smooth. It's give you positive cross currents, but in general, they are not dense in the space of currents. So this is a difference between the case of positive cross current and the case of probability measure. You don't have the density of smooth positive cross current in this space of current. Okay, I come back to this quickly. But let's discuss a little bit about the intersection of currents, or wedge product is the same. So what we expect to have in this setting So let's take an example of subvarieties. So let's say V and B prime are subvariety of codimension P and P prime. We assume that the sum of P and P prime is smaller or equal to K. Otherwise, generically, you don't have intersection. But assume that the dimension are big enough so that you can expect some intersection. So now, assume that the intersection of V and B prime is of codimension P plus P prime. This is a generic situation. So if you take a V of codimension P, B prime with codimension P prime, then generically you have something of the intersection will be of codimension P plus P prime. So in this case, in the complex setting, you can define the multiplicities of the intersection, and then you can define the currents. So V give you a currents, V prime give you current, the intersection give you currents, and then the intersection of V and B prime is given by this by the intersection of analytic or algebraic set here. Okay, so this definition is compatible with the definition in the complex geometry. However, it's possible that the codimension of V and B prime is smaller than P plus P prime. So imagine that you are in dimension 4, complex 4. You have two space of dimension 2. So generically, the intersection is finite. 2 and 2 in dimension 4, finite. But sometimes the intersection could be of dimension 1 or more than 1. So in this case, we say that we have some dimension excess. We have this. So we have to handle a situation. Smooth case. If you have smooth case, then the intersection of T and T plus is just equal to the West product of differential form. The same operation as for differential form is the same. Okay, so some problem for this theory is, I mean, the main problem is to establish calculus with positive cross current, but including the regularization. So how to approximate them by smooth one, which are easier to compute, and you cannot always define the intersection like that. So we want to find conditions so that you can intersect currents. And then the dimension excess also, you have to take care of this. All of them are very useful in dynamics. So actually, the first motivation we have come from the dynamic, complex dynamic. Okay, so let me discuss the first question. So again, in the compact Kähler manifold, and we have positive closed current T. And as I said before, you cannot regularize T in general. You cannot do that. But if you accept, you can only write T at T plus and minus T minus, and each of them can be approximated by smooth positive closed current. We can do that. So it's due to a consequence of the Smillie theorem for P equal to 1, and by Sibony and myself in higher codimension. So roughly speaking, and you control the mass of all of them. So roughly speaking, if you want to regularize positive closed current, you have to accept to lose the positivity. If you accept losing positivity, then you can do that. But you can control everything. You cannot avoid it. So it's like a moving lemma in algebraic geometry. And actually T plus and T minus, you can construct them explicitly, and this is actually important for applications. Okay, so we can regularize them. So it's useful for computation with positive closed currents. Now another point in the theory is the notion of potential. So now I come back to what I said before. So why the higher dimension, we have problem with higher dimension, or more precisely higher codimension. So consider a positive closed current of by degree 1, 1. So it's like a hypersurface in a complex manifold. So you have an operator, which is DDC, or basically IDD bar, which is similar to some Laplacian operator, such that you can basically write T equal to the Laplacian of U, some function. Okay, you don't need to care too much about alpha here, because we have to choose some alpha because of a cohomological reason, but it's not the most important point here. But the most important point here is that T is equal to the Laplacian of some function. So like E dimension 1, every measure is a Laplacian of some subharmonic function. Here also, we can write T as a Laplacian of function. And this is a key point in the theory for by degree 1, 1, which is very developed. The main point here is that working with function is simpler than working directly with currents. So that for 1, 1 current, people know many things about 1, 1 currents, and less for PP currents. Okay, so we cannot do that in higher dimension. So roughly speaking, you can try to solve the DD bar equation, but here you don't have something canonical. It's not unique, and so on. There are many problems. You cannot do that in the same way. So the way that we do is that to introduce another function that we call superpotential of our current T. So I'm not going to give you the formal definition, but basically we consider some space of currents, which is look like a compact complex manifold in infinite dimension. And then you have a function associated to the current. So ut is a function here, which is similar to some quasi subharmonic function, purely subharmonic function on this space of infinite dimension is compact, and so on, so on. And this function is canonical, and then we can study the current using this function in somehow similar way as we can do for the potential in the case of by degree 1, 1. Yes. A Kähler manifold, compact Kähler manifold. Yeah. Okay, if it's not compact, but you put hypothesis on the support of current, then you can also try to do that. So the important point is that the intersection of test current and yield current should be compact or convex enough, something like that. Okay. Yes. So okay, it might be a little bit surprising, but let me give you an example showing that actually we can do that. So one of the most important estimates in the case of finite dimension. The finite dimension, if you take, okay, T, so by degree 1, 1, you take the potential of U as before. So we can forget about alpha, it's not very important. Then you have some estimates like that. So the integrand of exponential of U is finite. So, okay, forget about alpha and C. Roughly speaking, you have some estimate here, which is exponentially stronger than L1 estimate. Let's say in this way. So it's exponentially better than L1 estimate. Okay. So now you can say that, okay, now we are in infinite dimension. We don't have Lyubich measure. You don't have something like that. So what you can do in this case, actually, you can do that. You can do that. So the statement is like that. So you take a superpotential at some value R. So you assume that R is regular enough, then you have this estimate. So without log is easy. So by putting log here, I have some estimate which is exponentially better than easy estimate that we can get. So it's similar to this one. Okay, so assume that you have U a subharmonic function. Then in general, you can have no estimate about, let's say, U0. You don't have estimate about U0. However, if you replace U by 0 by some probability measure, so smooth probability measure, which means that instead of this value, you consider the integrand of U d, let's say R, like that, so something like that, with R smooth enough. Then you have some estimate. Okay, then you have some estimate. But actually, Skoda tell you that actually the easy estimate that you can get is exponentially weaker than what he can get. Okay, so similarly for current, if you assume that R is regular enough, there's some regularity for R, then you have something like that, which is exponentially better than easy estimate that you can have. Chinda. Oh yeah, you have some constant. Yes. You have some constant. Yes. Okay, so we can you can now repeat the proof of Fornaess Sibony, and then you can, okay, so this is another problem, but you can prove this theorem by the uniqueness of G plus. The same proof at dimension 2, except now you have to use this superpotential and so on. And then we can use this to prove the exponential mixing of mu and then central limit theorem. This is also funny, this story, because we actually exponential mixing of own order implies the central limit theorem, but we didn't know that. So we proved this by ourselves. Then later we discovered that some people, other people already proved this before us. But actually exponential mixing of own order implies the central limit theorem. Yes. Okay, so this is the application of the this technique. Another technique that we use is the density of currents. So so starting point here that we want to study the intersection possibly with dimension excess. This is not. This wasn't done before. People always try to avoid this situation. Pluripotential theory, we except the long number theory. So what is the point here? So we assume that we might have the dimension excess between the intersection of varieties. This is that's easy to see, but now given two positive closed currents, so how you can say that, okay, there's some dimension excess in this intersection, because it's difficult to draw currents. But then we try to do that. Okay, the idea is extremely simple. The starting point is very simple, but then technically it's quite complicated. So let me summarize here the idea. Oops. So assume that you have two sets, A and B, inside X, and then you want to study the intersection of A and B. And then the way that we see this is you can identify this with the Cartesian product of A and B, and you take the intersection with the diagonal. These are diagonal in X2. Okay, so here is X2. Here's a diagonal. Okay, so now you want to study the intersection of A and B. You just take the product. Yes. Okay, so something like that, and you take the intersection with the diagonal. Okay, so for the moment you say that it's the same. You don't see anything different. But then the idea is that, so if you want to see this intersection, what you can do, you can dilate the, so let's say delta is here. So we can dilate the coordinate in the normal direction. So you zoom this in the normal direction, you dilate them. So somehow you see your object more clearly. You zoom this. And then you can take the limit. So you dilate it by z map to lambda z, and you take lambda going to infinity, and you see the limits, and you say that, okay, you expect that it's easy to see the intersection. Actually, you do the same for currents. So in sheet of A, you put one current. In the sheet of S, you put another current. The Cartesian, there is no problem. It's a duality of the Weierstrass approximation theorem. Then you dilate the coordinates. So this now is a problem. How? What is the meaning of dilating the coordinates? You don't have something like that. So you have to bring everything to the London. You bring them here by some map, homomorphism, diffeomorphism. But in general, you cannot have a holomorphic map like that. It doesn't exist in general. So you can bring them to this picture of a normal bundle, vector bundle of delta. But you have to use some map which is not holomorphic, but you can choose the one which is close to holomorphic, which means that you take the derivative on the diagonal, you have some C-linear map. Okay, assume that you do that. And then you have many parameters. You have tau here, you have lambda there. You dilate the coordinate, you take a limit, and so on, so on. Then you have to show that the object that you construct in the limit is independent of all the choice that you have here, and this is quite technical, but it's true, and you can do that. And then when you do that, you see the limit, and you see, and you can decide if you have the dimension excess or not. And if there is no dimension excess, you can say that if you can define the intersection or not, and so on, so on. And we expect that this give you one of the weakest setting where you can define intersection and so on. So as I say, it's a generalization of the theory of the long number where S is a Dirac mass. If the second current is just a Dirac mass, then you get the long theory, which is not formulated in this way, but is equivalent. Okay, so this is a problem of de Mailly, how to define the intersection of current of higher by degree, and we can use this theory to do that. I skip it, but so the motivation for this theory is following theorem that I stated before. So the sudden periodic points are equidistributed with respect to mu. So how to prove this? So here's a picture. So we can identify the periodic points as the intersection of the graph of Fn, gamma n with the diagonal. And then basically the graph will converge. You normalize this in a good way, then the graph gamma n, when n go to infinity, you have a good limit. And then the problem becomes that in this situation, can we have the intersection of limit is equal to limit of intersection? This is not true in general. I mean, outside the dynamical system is not true. Here is true, but why is true? So if you want to show something like that, you need some kind of transversality between the graph gamma n and delta. So strictly speaking, you cannot have transversality in general because you might have tangency and so on. And even if you don't have tangency, you can have almost tangency. It's already some problem. So what you have to do, you have to quantify the transversality in some sense and show that when n goes to infinity, the transversality and non-transversality go to 0. And then we use the theory that I developed here to show that actually this is the case. When n go to infinity, the non-transversality go to 0, and then we get the equidistribution theorem. Okay, thank you very much.